recording sessions. We have one person who is absent. Yes, discussion is always longer than the introduction. For today's experiment, the purpose of the title for the experiment is recrystallization. Can you tell me what is the purpose of the experiment? Why do we have to do recrystallization? What is the purpose of recrystallization? Purpose for recrystallization: purify a crude product. Very good. If you have chemical reaction, like the chemical reactions that you are performing today is the reaction of aniline with acetic anhydride that will produces acetanolite and acetic acid. So the desired compound for us is a pure acetanolite. So if we have two reactants, and sometimes we do have a catalyst, or if you have like more than two reactants, then we don't have always a fixed upper ratio that everything is going to be consumed entirely. We will have like excess compound, we would have limiting reactant. Ideally, the limiting reactant should be consumed in a chemical reaction, but you should always have extra of the excess compound. You should never expect like one compound as a product unless you are doing simple like combination reaction for general chemistry. So if you have more than one product, you have leftover of the reactant. So when your reaction is complete, then you have the product, but that product is not a pure product, that is like crude product. To recrystallize the sample, the product, you have to follow a designed experiment already based on the compound that you are trying to purify. Or if you know the name of the compound, you have to do a lot of trial and errors in order to find the proper solvent, and you recrystallize your compound from its impurities. Another time application would be if your sample is a solid compound, you measure the melting point and you get a broad range of melting. When you have a broad range of melting, that means your compound is not pure. Then you have to purify your sample before you can identify your sample. Now, what are the characteristics for a proper recrystallization solvent? Because you have to first choose a proper solvent. This is a procedure that is given to you for recrystallization, is already proven by someone else. What are characteristics for proper recrystallization solvent? The product would be very soluble at very high temperature or at the boiling point of the solvent, but it would be insoluble at low temperature. So it doesn't dissolve at the low temperature. So you can, when you lower the temperature, you can get the crystals back. When you say it doesn't dissolve, that means you are getting the crystals back. Crystals are coming, settling down, forming the solid compound. So it doesn't dissolve, it doesn't stain the solution anymore when you lower the temperature. At the high temperature or boiling point, your sample must dissolve in the solvent at a high temperature. The other condition or characteristic that you mentioned, it should not react with your sample. Like for acetanolite, the solvent that we are using as recrystallization today, it should not react with it, should not have chemical reaction, because chemical reactions are irreversible process. So if your compound reacts with the solvent, it's going to generate a new compound again that is irreversible by physical means. You cannot get it back to original compound that you wanted. So it should not dissolve. That is right. Now, with respect to impurities, how should solvent react? With respect to impurities. So with respect to compound, It should dissolve at high temperature, but should not dissolve at low temperature. So your sample, the desired compound, should be insoluble at low temperature, but soluble at high temperature. What about the impurities? What should the impurities, how should the impurities react in that solvent? Or what should be the characteristic or solubility characteristic for your solvent with respect to impurities? Because if the same thing happens to impurities, if impurities dissolve at high temperature but they don't dissolve at low temperature, then you are going to get them back again, right? Insoluble in boiling solvent, very good. So impurities should not be soluble at all. So when sample dissolves, then the impurities should stay in the solid form. It doesn't dissolve at a high temperature. And in that case, you are going to set up hot filtration, which is a gravity filtration. And using a hot filtration, you only use the hot filtration if you have insoluble impurities. And what does insoluble impurity means? Means that at the boiling point of your solvent, you see that you still have pieces in there that could only be impurities that didn't dissolve. So you do hot filtration. Why should be hot filtration? What is hot filtration? Hot filtration means that your setup for filtration is going to be hot, and you filter it while your sample is hot. And in that case, you do not get premature crystals. That means if your funnel, for gravity filtration, and the paper that is in there is cold, as soon as you pour the mixture into it, it's going to cool down and your sample is going to crystallize inside the filter paper, and that's not what you wanted. So you want to keep your system hot, so when you pour hot solvent, the solution, it will pass through that contains your compound, your original compound or desired compound. Your compound should not stay in filter paper. That is known as premature crystallization. So the solvent should not dissolve insoluble impurities, and if you have insoluble impurities, you would separate them by hot filtration. Or your sample dissolves at high temperature, you get it back at cold temperature, but impurities, if it dissolves in high temperature, it should stay soluble, and when you cool down the solvent, the impurities should stay in the solution and it should not go back to crystals again. So with respect to two separate aspects. With respect to sample, which is desired sample you want to recrystallize, your sample must dissolve at high temperature and not dissolve at low temperature. For impurities, it's two scenarios. Either it never dissolves, so you separate by gravity filtration, or it dissolves at high temperature and it stays soluble, and when you lower the temperature, it doesn't come back to the solution, or it dissolves at cold solvent, to summarize it. So when you have your proper crystallization solvent, then you are going to add the solvent to your sample, heat it up to the boiling to make sure that your sample dissolves, or you keep adding hot solvent to dissolve your product or the sample at hot solvent. Then you are going to, if you see insoluble impurity, you do gravity filtration. If not, you are going to just let it cool down at room temperature. You don't want to place it in ice right away. What is problem with placing your sample in ice? You take it from hot plate and you place in ice right away. What would be the problem with that? A sudden cooling of the solution is going to cause problem. What is the problem? You have to cool down the solution to room temperature first before you put in the ice bath. Very good. If you do a sudden cooling, you take your sample from hot water and then a hot plate or heating up or hot water bath, or when it dissolves, and you place it right away inside ice bath, basically precipitation will take place. Your solid is going to precipitate all of a sudden, and it would go to solid phase, and at the same time that it's coming down, it can also bring impurities down. So you would get impurities trapped within your sample. So you're not going to get pure product. It can also trap solvent. So if it traps solvent, that means that the term of trapping solvent by your sample is like oiling. So you cool it down, you see particles of oil, pieces of oil floating. That means your cooling process was not efficient. Basically, it wasn't like slow cooling. With the slow cooling, you should not get any oiling because it's not going to trap the solvent. So you get actually solid come down. The other advantage of slow cooling or cooling to room temperature is the size of crystals, which is understood is the opposite to precipitation. You actually get crystallization. And for crystals to form, they must have time to stack over one another. So if you give time to crystals with slow cooling, you're going to have better stacking of the molecules over one another to form perfect shape of crystals. You get large crystals, then it doesn't trap impurity, it doesn't trap solvent. And if you have large crystals, based on what you have read in the experiment, in the last step, we have a vacuum filtration. For the vacuum filtration, if you have precipitate, which is like small size of crystals or compound, is going to stuck in the opening of the filter paper. It doesn't go through easily. It would take longer. The drying part is going to take longer. And but if you have large crystals, filtration is much easier, is more efficient, and solvent is removed entirely. Drying of the sample is going to be easier. And if your sample is dry, is going to give you better melting point. If your sample is not dry, the solvent counts as impurity, and then your sample is going to melt at very low temperature compared to the literature value. So the choosing of solvent is important. Heating up to boiling to dissolve the sample is necessary, because if you choose your solvent properly, your sample is going to boil at high temperature, not at lower temperature. Then you're going to cool down slowly, and when you cool down slowly, you should see the crystals forming first before you place that in the ice bath. Now, you do everything based on the procedure. You cool it down. You don't see crystals. What you have to do in order to induce crystallization? What are the tricks that you could use in an organic lab to induce crystallization? This means that your sample has been heated, it's been cooled down to room temperature, you place an ice, and you don't see any crystals forming. What could you do? Seed crystals cool in ice bath for longer, so continuous cooling. So you cool it further to lower temperature, hoping that since solubility is low at low temperature, then at lower temperature you would get your crystals back. If you don't get crystals and the temperature is very low, there is a chance of supersaturation. And if you have a chance of supersaturation, that means is that you are not getting crystals, but your solution is still saturated. You have to seed the crystals. How would you seed crystals? There are a few tricks to that. One, you can add piece of a few crystals or few grains of the pure sample. That's the case that you already have pure sample in the lab. You add it into your solution, and then because it's a supersaturated, it's going to crystallize right away, and every particle of the sample is going to come down in the solid form. If you don't have any pure sample, what you do, you take a stirring rod and you are going to scratch the inside of the wall of the glass that you have your solution in. When you scratch it, you basically are scraping crystals or tiny particles of the glass you are dropping into the solution that acts as a seed. Other times, you can dip your stirring rod into the solution. Because a solution is mixture of solid and liquid, you take the stirring rod out, you let it dry. When you let it dry, the solvent is going to evaporate from the surface. You end up with like a dark or powder, or it doesn't have to be the dark color, so it's not clear glass anymore. When you see that, it's like a dull color, or it's a powder state or crystals attached to the tip of the stirring rod. You place that back into the solution, and those particles is going to detach and go into the solution and act as seeds for crystals. And that's the cleanest part, and it's easy. You don't put any glass in there. You don't have to get crystals. And sometimes you do all of this and you don't get crystals still. What could be the problem in that case? If you do all of this and you don't get crystals, then it means your solution is not saturated. If you have unsaturated solution, you cannot make crystals. You cannot get the crystals back. So if you use too much solvent to begin with to dissolve your sample, and that was just by mistake you used too much solvent, your solution is not saturated. Now you have to lower the volume. How would you lower the volume of the solvent? Can you pour some out? Would that make the solution saturated? Yes or no? How would you saturate a solution that is not saturated? If you pour some out, obviously, it was just probably a silly joke. It's not going to saturate the solution that is remaining here. How would you saturate the solution if it's unsaturated? You place this back on a hot plate, you heat it up, and when you heat it up for long enough, you would reduce the volume in half. Your solution is going to be saturated, and when it is saturated, now you cool it down again to room temperature to get the initial crystals. Then you place an ice for complete crystallization. What is the purpose of using charcoal in recrystallization? Is that one of the pre-lab questions? Using of charcoal. Charcoal, activated charcoal. It removes the colored impurity. Activated charcoal can remove colored impurities, and with the colored impurity being removed, is going to be now colorless, or not colorless, the original color. So if your impurities is like colored, then you can use the activated charcoal. If your solution looks clear to you, you don't have to use charcoal if you don't have impurities that like colored impurities, because the charcoal is like gray color, and even though your filtration, like for gravity filtration, unless you use like special filter paper, some of those particles can pass through and it will make the color of the crystals gray color rather than the white color in this case. So if you don't see like obvious color that it's been added to your sample, like you were expecting like white color, now it's like a green color or yellow color or red color, you don't have to use activated charcoal, sorry. But if you have impurities that are colored, then you would use charcoal, activated charcoal to remove it. Okay, one of the pictures that I want you to take, this is just silly, it's not part of the experiment either, but is a proof that you have been on your camera at this point. Take a screenshot, take a picture of this diagram, and include that as your first picture of the experiment. I don't know, you can do a screenshot or you can do use your cell phone to take a picture. Your picture doesn't have to be 100% clear, but it has to be a picture of what I'm showing to you as your first picture. And if one of you can tell me if a screenshot is easier or using a cell phone, so next time when I'm asking, I'm just going to say, use your cell phone to take the picture or do a screenshot. Which one is easier? A screenshot? Perfect. Okay. You could do a screenshot of that, and that would be the first picture that I expect for your lab report number 3 as a separate file. So please screenshot and take the picture. It's going to be like 3 or 4 or 5 of them, and I want to make sure that you are all including that in your and it would be different for different, of course, different experiments. So, do you have any questions from pre-lab assignments for me? Do you have any questions for procedure? Because I'm about to start the experiment, and we talk and explain at the time of the experiment as well. Do you have any questions for me? No? The data table for this experiment is mass of the reactant. Basically, you have the volume of the reactant. You use density later to find the mass per reactant. Then you have your the percent yield or percent recovery. To calculate percent recovery, on page 31 of your lab manual. Page 31 of your lab manual, you are going to use the volume in this case, and then use the density. Density times volume, it would give you mass for your reactant. And then use molar mass of your reactant to find the moles of reactant. Use the ratio or mole ratio of product over reactant, using that from the balanced equation. In this equation is a 1-to-1 ratio, so 1 mole of product over 1 mole of the reactant. If you have mole of the product multiplied by the molar mass of the product, that would give you theoretical yield. Theoretical yield, it would be used, like this procedure in page 31 is used to calculate theoretical yield. Actual yield is the mass of the product at the end of the experiment. So when we have the sample already filtered, dry, and before measuring the melting point, you put it on the balance and you record the mass for your product. That would be the actual. And actual divided by theoretical, that gives you percent yield. So you should include in the abstract. Melting point and percent yield should go into abstract. It should go into conclusion, and it should be also in discussion. So you are using the data value in multiple places. Now, let's follow the procedure and perform the experiment. In a 250 milliliter flask, I'm going to add the 4 milliliters of aniline. I brought the aniline to the station, so I'm going to add the 4 milliliters of the aniline. And what else should I add? What else should I add to the aniline? What's next based on your procedure? Add 30 milliliters of water. Okay. Going to add 30 milliliters of water. and we are going to mix it well. Then we are adding the 5 milliliters of the acetic acid in a small portion. Practice. So I'm going to add the acetic acid in a small portion and mix it well. While I'm adding. See the white powder is forming? That is the product of the acetanolite that is forming. Okay. For the powder forming, take a screenshot of the reaction mixture. Include picture number 2 for the reaction. Just take a screenshot. Everyone has a screenshot? Very good. Please do not share the pictures because I can see the original. Everyone? No? Okay, please take a screenshot. Do not share the screenshot because this is just showing the people have paid attention and they were following the experiment, and I can check the originality of the pictures, and I do not like shared picture for this experiment. So if you share with someone else, you be in trouble. This is not to catch people, you know, cheating. This is just to make sure that everyone follows the experiment. Okay. Next step. Now we have the product, and in the same reaction mixture, I'm going to add my crystallization solvent and crystallize this crude product. Now, my crude product, it should have like a lighter or more white color. With the white color, now it looks like more of a tan color. So I need to recrystallize this to make sure that I'm getting the color that is desired. Because I'm trying to boil this, I'm going to have to add a boiling chips. The same reason we add boiling chips for flask to the boiling flask in distillation. We are going to use boiling chips for any time we are boiling liquid to avoid bumping. So I'm going to add a boiling chips. Just make sure you see the setup. We're going to add a boiling chips. And I remove this later on mechanically. I don't have to filter it. Add the 100 ml of water. and let it boil. Heat up to boiling. I usually warn the students in this step when this solution it reaches the boiling point. If you don't stop it right away, it's going to foam out and you lose the chemical. So as soon as you see like clear solution, you should stop boiling. Occasional stirring is going to help, but we understand that stirring is not the factor here for dissolving is the temperature, because we chose a proper recrystallization solvent that is going to increase the solubility as the temperature increases. So when the temperature increases, is going to be increase in solubility, the sample should dissolve. So occasional stirring is fine, but constant stirring not necessary. So we wait until it dissolves. We get the clear solution, then I have to take it right away and place it on the bench top for it to cool down to room temperature. When I see the crystals, then I use the ice bath. So while I'm waiting for this, I can go ahead and prepare my equipment for the next step, which is preparation of the ice bath. Use copper pot for the ice bath. So just simply add ice to the copper pot. And also, I need cold water for later on. I need ice bath for my crystals. I also need cold water for my crystals to wash them when I'm doing vacuum filtration. So I place a container of water in the ice chest to make sure that it's cold enough for me to use it later. So I have my ice bath ready. I add some water so it's easier for the beaker to sit in there. Just getting ready for later. Okay, while we are waiting for the solution to form, basically the solid needs to dissolve for the solution to form, I'm going to talk about vacuum filtration system that we have. A vacuum filtration we have, it's made of a Buchner funnel and vacuum flask is a flask with the side arm, which we can connect this one to vacuum system, and when we pour the solution, it can pull the solution, the solvent by force for maximum efficiency and faster filtration. Since the opening of the Buchner funnel is large, we must use a filter paper. The size of the filter paper, it depends on the size of the funnel. And we need to often, if this is the same filter paper that we are going to use our product, is going to stay on that, it needs to be pre-weighed. So if we pre-weigh our filter, then we can weigh it with the sample, get the mass of the sample at the end by subtraction. When you place the filter paper, it should cover all the openings, and you can add few drops of the solvent, in this case is water, to make it stay still, because if it's loose, the mixture can go underneath and then you lose your sample. So before I make this paper wet, I need to measure the mass. We also have another component to our system here in this lab, not every lab is using, is a trap. A trap it goes between the vacuum flask and actually the vacuum. We have the vacuum pump downstairs. We turn on this when it's on. We turn on the vacuum, and vacuum is applied. Today the vacuum is off. The vacuum system is off. So I'm going to use a vacuum pump. So I'm using a pump as the using a pump for vacuum is a smaller uh, device to create the vacuum. So the vacuum is not as strong, but it does work perfectly for our experiment. The purpose of trap is to make sure that there is no liquid going into the vacuum pump, because vacuum pump is electronic. You don't want to put any water in the electronic. So the when we have the trap, if there is any liquid that goes down, it can be trapped in the trap before it goes into the vacuum system. Sometimes you have too much solvent, but you should never use the flask more than like 2/3. As soon as the 2/3 of the flask is filled up with the liquid, with the filter, you have to stop the vacuum, pour the liquid out, and then use it again. And when you are done with the experiment, this setup, it should go back to the right assembly. You want to make sure everything is in place, and you put it back. There's a cabinet here. It's called vacuum system. You place in the cabinet normally. It doesn't stay out all the time. I'm going to measure the mass of the filter paper with a watch glass. So I want you to record that number. First, with care. I don't know if you have used the balance already or not. I don't think for this experiment, right? For you haven't used for organic the balance. So we are going to press the tear and watch glass plus the filter paper. And please take a screenshot. Can you see the number? Take a screenshot of that number. And if you can not see, you let me know. Did everyone take a screenshot? Perfect. And that number is going to be a numerical value for you, for your experiment today, that you are using for the for your data. What was that number? It was 49.962. 957. Okay, I record that number. That is the same mass of the aniline? No, it's just the empty filter paper and the watch glass. We don't have the mass for aniline. What did we use? Instead of the mass for aniline, we used 4 milliliters. And if you check the step number 1 on the procedure, is asking us to use the density, which is a literature value. You find the density for aniline, and you are going to convert the volume to mass. Multiply the volume by density, that gives you the mass for product. This is the filter paper plus the filter paper plus watch glass. I don't want my sample to foam out, so that's why I don't want to put too much heat, but at the same time, we need the sample to dissolve. So I'm setting up the hot plate between 7 and 8. Okay. Any questions for me? Question? No? The crude product, no. We don't need the crude product. We just need the mass for the final product after the recrystallization, after drying of the sample. You're welcome. Let me open the chat so I can read the questions. Maybe I missed one. The same number that you used for when you took the screenshot, whatever number you used, you had from the screenshot, you would use that number, right? What was it, 957? If that was 957, 49.957, you use that number for then you have mass of the crude, we don't need it. And I have your screenshot. Yes, that's what you use. Yes. The difference in the number is not going to be huge when it comes to like calculation. The balance that they are using is very sensitive, and I can take the camera again there, and I show you how sensitive this is. You see, like I move my hand over, that number is changing. So with a little bit of pressure. So maybe when you took the screenshot, like my hand was this much close. We usually step back, we wait for the number to stabilize. And sometimes even being AC being on, blowing air, it can change that number. So, but it's going between 55 and then 0.965. So any number that you have in a screenshot, that would be valid number to use. That's good. It's getting close, but not yet. I have it between 7 and 8 because I was just, since I was moving to the scale, I lowered it to 1 and 2 because I didn't want any splashes while I'm showing you the scale. I came back and I put it back again between 7 and 8. 6 and 7, but we don't want it like too high. We don't want it 9 and 10. We don't want it 1 and 2. because we want it to boil, but at the same time we don't want it to foam out. Okay, do you see the sample being dissolved? Could you see that there is no white powder in there? Yes? Okay. So the sample is dissolved. Just have like very tiny piece of oil particle and make sure that it's gone. And now take it out and place it on the bench top. Turn off the hot plate. I don't need the hot plate anymore. And wait until I see some crystals forming. When the crystals form, then we can place in the ice bath. Let's see if I can put white paper. Maybe it's easier to see for you underneath. And I want to show you what I was talking about when you take the stirring rod out. Since you have a solution, mixture of solid and liquid, the solid will remain on the stirring rod, and the liquid portion is going to evaporate. So you basically, after the solvent is evaporated, see, it's not clear anymore. You have some white powder right there on the edges at the end of this stirring rod. And when I place this back in, they act as seeds for the crystals. So you could see the seeds or tiny particles. And if I scrape it here, you could actually see pieces on the edge of the watch glass. That's all we need, just a small, very tiny piece of the part. pieces of particles, which is going to be good enough for crystals to form. It's too hot yet, so I don't expect the crystals to form. At the same time, is a good solvent is not going to take too long for it to form. And when I see the crystals, then I can actually place an ice bath. Do you have any questions from the experiment 2? Any problems, any difficulty? Sure. You see, it's changing. The number that you have is fine. Whatever number you have is under 100th place is going to is acceptable now. Okay. Alex says attendance. Andrea. Brianna. Brittany. Brittany Ann. Brittany A, okay. And Brittany B. Farah. Jermaine. Jermaine. Jermaine is absent. Janica. Caitlin. Kelvin. Lindsay. Charlene. Okay. Jermaine is not present and Jermaine is not present. The screenshots, yes. You make a file with just the pictures and you would say images or pictures file. It would be same, so two submission to the same folder. So one is a lab report and one is the pictures. What I'd be looking for is that there is no originality based on the, the device that took the screenshot, and also the timing. The timing is supposed to be also during the lab time, because later on when the video comes, students can actually take a picture of it from the video, but the time of the screenshot, it should be the lab time, and the originality also should not match, should not be similar to someone else's. So please not share the screenshots. Thank you. You don't have the time on the picture, but I can, when I'm doing analysis, because I had to use this for other labs that is online, I find the time that was taken. So it will give me the information. You don't have to have the time at all. Okay. I don't know if it's visible to you or not, but I want to see if you can tell me, you see those particles that are forming as crystals at this point? I don't know what type of background is going to help. Definitely not this one, right? That one, maybe a white one or black one. Is white background better? Can you see any particles moving? Any solid forming? Yes? So you see those particles that are forming? This is actually a nice a screenshot. You could take the screenshot when the particles are coming back into from the solution, they're coming out. You could take a screenshot of this, showing that crystals are forming. We don't have complete crystallization, but the crystals started to form. Is a good time to place in ice bath at this time. Okay. I want to just make sure that you see the particles or the crystals that are forming, and it's flaky, so it didn't precipitate all, settle down. Then we can place it now in the ice bath. So I place in ice bath. I have my own rule here for the ice, the timing for the ice bath. I use like I don't know how many of you remember from the subway when they were saying like advertisements with the 555. I guess how much is what was it? Well, 5 was like 5. It says $5 for 5 inches, something, or foot long $5. So I have my 555. So it's 5 minutes timing for the ice bath. That gives enough time for the solution, if it's immersed in the ice. Maybe this one looks better. I mean, people are really, students, when they are in the lab, they really like this texture here. That crystals are forming. It's very clear that crystals are forming and they're floating. Nice size of crystals. So when you put 5 minutes in the ice, it's going to complete the crystallization. The temperature would be low enough to form the crystals. Then it would be 5 minutes vacuum. I run the vacuum for 5 minutes to make sure the solvent is removed completely. And 5 minutes in the oven that is set for 100 degrees Celsius. Okay, for the procedure, you just see that it's 100 degrees Celsius. But when I design the experiment, when I talk about like design of this experiment, I make sure the setting of the oven is the boiling point of the solvent, In this case, the solvent is water. Water boils at 100 degrees Celsius and is less than melting point of the crystals. If I use the melting point, if I set the oven temperature high, basically at the melting point of the crystals or close to melting point of crystals, then my crystal is going to be melted in the oven. So I have to make sure that the heat is sufficient enough to evaporate the solvent. At the same time, it doesn't melt the crystals. So the melting point of the crystals, anybody has the melting point for crystals? The melting point for the crystals, you can search it up, please. Acetanolite. Let me know what is the melting point for crystals. Because I usually ask the students to get it for their own experiment. So I do not like to include in the lab manual. So you learn how to use you just type the acetanolite physical property or melting point for acetanolite and you get it. But in the past, when we didn't have the internet available all the time, this was the book with the literature value for the chemicals that we were using in the lab, and the students were actually required to look the values through these books. Now that you have the internet, you just search it up and you give me the value for acetanolite. Did anybody find the acetanolite? Isn't acetanolite the crude product? Even if the acetanolite is the crude product when it's still mixed with the solvent, when it's still mixed with leftover of the reactant, but after you crystallize it, it's going to be pure acetanolite. So we are looking for melting point of acetanolite actually. So do you have the melting point? 113 to 114, good. So if it's 113 to 114, we cannot have the setting for oven too high. So it has to stay around 100.
And then there were two. I know. You know what? Nobody likes us. The two bitches are left. And then
Your mic is on. Turn off your mic, please. You could turn on your mic, Brittany, to ask questions, but when you are not asking questions, please turn off your mic. Thank you, Brittany. Okay. So this book is actually very old. Every year they come up with a new edition. This is the 48. Looks like really, really old because what I have in the office, in my office is 84, and that's not the newest one. 84 probably still like 10 years old. So the book that I have is thicker and larger than this. Means that every year new compound is being added to this book. So this is called the CRC Handbook or Chemistry and Physics Handbook. Physical property and chemical reaction for all known chemicals is recorded in a hard copy of the CRC book, even though you have it online. Has it been 5 minutes? Yes, looks like it, right? So we are going to place the filter paper inside the vacuum. Vacuum funnel or the Buchner funnel. Attach the vacuum to the vacuum pump. This is the vacuum pump. When I turn it on, it pulls the air and it creates vacuum. So I attach the the vacuum flask to the vacuum pump using a trap. Turn on the vacuum. Use some cold water to make the paper wet, because when the paper is wet, it will stay still and it doesn't allow the particles to go underneath. Because I want to transfer all the solid into the funnel, I have to mix it, because if not, only the liquid portion would go and most of the solid would stay. So I keep mixing and pouring into the Buchner funnel. If there is any leftover in the flask, I use the cold water, ice cold water. This has been placed in the ice bath for a long time and it's really cold. Why does it have to be cold? Because I do not want to melt my sample at this point. If the water is room temperature, some of this sample is going to melt. If it's hot, all of it is going to melt. But if it's cold, minimum amount of the solvent is going to melt. So I use cold water to wash the crystals and time it now. We wait for 5 minutes. I'm done with the ice bath. Only water can be disposed in the waterway down in the center. All the chemicals should be disposed properly. We do have a filter with the containers properly labeled for disposal. And I'm going to show you these containers here. We have hazardous waste for solid waste, halogenated, so that means it's organic compound, but it doesn't have chlorine, bromine, or iodine. I'm sorry, halogenated would be the ones that they contain chlorine, bromine, or iodine. Aqueous waste, anything that is water soluble, not organic compounds like acids and bases, would be disposed into aqueous waste. And then we have non-halogenated waste. These are organic molecules that they do not have halogens or chlorine, bromine, or one of the halides. The halogenated, they do contain halogens. Non-halogenated doesn't contain halogens. We have the oven, 2 of these ovens, and this one is set at high temperature now, boiling point of the solvent. And after the 5 minutes is over, I bring it and I place it in the oven. It's been turned on. At the end of this experiment, after we have a dry sample, we need to measure the melting point. So I'm going to actually get a melting point apparatus, place it, set it up here, so you could see, performing the melting point again with the final product. When it's 5 minutes, you could warn me. You could tell me it's been 5 minutes, and I start I would take it and place it in the oven. Did you time it? Because I didn't. 3 minutes left. Okay. Thank you. As long as you have it timed. Okay, I actually changed my mind. I was going to bring the melt pump here, but since I'm using a laptop, it's more flexible. I can take the laptop to the instrument room and we do the melting point here after it's dry. The vacuum is not very strong, but it's okay. Okay. Has it been 5 minutes? Yes. Okay. So we take the sample and we place on a watch glass, same way that you would bring cake out of the oven. Sometimes you just flip it and you get the paper with the cake, like you flip it. Other times you can just slide and get the filter paper or the paper that you have for the cooking paper underneath. It just comes, you slide it, you take it out of the container and you place in the watch glass. You place the sample. I'm going to take the sample, place the sample in the oven. Okay. Going to place in the oven. And you can time it now. As soon as it's 5 minutes, we take it out of the oven and we check the melting point. If it starts melting below 100, that means your sample is not dry. Basically, it dissolved in the water that was in there. If it melts less than 100, then we have to put it back in the oven to dry. But if it melts higher than 100, then we are sure that it's dry enough. I don't know how many of you noticed, but I had very tiny sample in another watch glass. I placed in the oven, so that sample is going to dry first. I can get busy with the melting point. As soon as that tiny sample is dry, I can start measuring the melting point and wait for the large sample to dry completely before I can get the mass for the top. Okay, any questions? No questions? Not yet? Okay. We keep missing one student here. I want to see if it's the same. Yes, same student. Jermaine, are you back? Yes. You know, I mark absent for you, I think, when I call for attendance. You didn't hear me, or you were, or I didn't hear you. Okay. But Shimon is not here. Came a couple of times and left. Okay. Going to take the laptop to the instrument room and then get the sample for melting point. Here's the instrument room with the melt temp apparatus. There I said we have them in the instrument room, those charts that are on the wall. And then we have other equipment that actually, some of them will be used for organic 1 and 2 for you. The IR machine, the polarimeter, and other equipment that we have. Sample, and I prepare the sample for you here. Same as last time that we measure the melting point. We have the sample, take a small capillary tube to feed the sample into the capillary tube. By dipping the open end of the sample into of the capillary tube into the sample. Not much of a sample, about 2 to 3 millimeters, less than 1 centimeter, like half centimeter. Pass it through the hollow glass tube a few times to get the sample all the way down. Place it down. I can place it into the sample holder of the melter apparatus, into the sample holder. What should be the setting? Do you remember from lab 1 what should the setting? By any chance? If it's between the melting point, since I already know is 113 to 14, then we look at this line here, 100, that's 150, and then we have between 4 and 5. Because the melting point is between 100 and 150, the setting should be between 4 and 5. So we set the melt temp power regulator between 4 and 5 here. And we wait, and we don't want to miss the melting point here. And make sure that record the melting point for initial melting and then for final melting. Okay, if you have any comments, any questions, at this point we have time. We're waiting for it to melt. If the sample melts close to 113, 114, that means we have a pure sample. The closer the melting point is to the literature value, the more pure the sample is. Sometimes we cannot expect exact number of 113 to 114 unless we are 100% sure that our thermometer is calibrated. Sometimes the thermometers are not calibrated, maybe like a couple degrees off. We try to start with the thermometer that is working. You should check the thermometer, like if the ink, like sometimes you see gap for the ink, then you want to make sure to not use that thermometer. Use the thermometer that doesn't have any gap. And to better test or calibrate this, you can place in pure water, boiling water. If it shows 100 degrees at sea level, then your thermometer is calibrated. If it's sea level and this one shows 95 degrees, that means it's 5 degrees off. Okay, the sample has not melted yet, and the temperature is 90 something, which is a good news, because if it dissolves below 100, that means the sample is not dry. Okay, it did pass 100 also. Definitely the sample is okay, it doesn't have any water. Okay, initial melting 109. Completely melted is 112. So 109, 112. Turn off the melting apparatus. Gonna take this sample because we need to combine with the other one for the mass. Go back to the main room. Okay, it's very hot. And because it's very hot, I'm going to get a clamp to take it. Okay, the sample looks dry and it has been 5 minutes. So I'm going to let it cool down slightly to room temperature before I place in the oven. I took very little sample for the melting, so I'm going to return it to make sure that when I'm measuring the mass, it measures everything. because it's cold enough. Now place it on the scale, and time for you to get another screenshot, please. The number doesn't show? Okay, let's see. I wasn't looking. Okay, does it show now? Okay, perfect. Please take a screenshot, and that would be your number for the mass of product, filter paper, and watch glass. You subtract the number you got earlier to get the mass for final product only. Everybody had a screenshot? Yes? No? Okay. Take a screenshot, please. Perfect. Yes. Yes, you had 4 screenshots, and those 4 screenshots you could copy them and paste in one, like one Word document that's just pictures, and then picture file, name it as picture file for experiment 2 or experiment 3 in this case, and you submit it to the same folder that you have your assignment, your lab report. So 2 separate, one pictures and one. The pictures, it counts for your attendance, your presence, your class participation. If you don't have the pictures doesn't have to be like perfect pictures, but it should be taken during the lab while you were watching the experiment. Is it distance learning? You know, I'm going to, I guess, stop the recording, but it's like just being, you know, honest. There are cases that student can turn on or join the meeting, leave, and then they're done with the lab. They come back 5-10 minutes later and leave the session. So this is just a trick that is used for online teaching. We are monitoring students' presence, being there, watching and following and participating in discussion. So it's not like a point system to say, okay, this one has separate point than the other. If you have no pictures, because you were asked to take pictures and you didn't take pictures, that means you were not present for the 4 times, you know, that we asked for pictures. Like, I understand if one picture is missed because you were not either paying attention or you had to take a break. Sometimes we do take a break during the lab because it's a long time, but you can't miss all the pictures. And that's why please do not share pictures, because then that affects the originality. And also make sure your pictures, you are submitting the pictures that you took during the lab, because the timing that you take the pictures also are important. The times is important. Due date. The lab for due date, whenever it's due, you turn in the lab. And this Friday, you don't have labs, so you have only 2 labs this week, and this today and Wednesday. So this week, you have 2 experiments only. Any questions for me? Let me stop recording. This doesn't mean that we are done with the lab. We do have remaining time for the lab, and we still have data analysis. We do have question answers, but I need to stop the, I'm going to stop the recording at this point, because for data analysis or your other questions, there's really no need for recording. And then you can use your mic for your question as well.